Welcome to this explainer. Today, we're diving straight into the fascinating, invisible physics of how natural gas behaves deep underground and exactly how engineers predict its flow. If you've ever wondered how we quantify and extract something we can't even see, trapped in solid rock thousands of feet beneath our feet, well, you are absolutely in the right place. Here is our roadmap for today. We'll be covering the DNA of natural gas, the real gas law, sour gas and realities, flowing through the rock, the turbulence factor, and finally, transient flow over time. Let's get right to it. Section 1. The DNA of natural gas. So, what exactly makes up the gas down there underground? Let's start at the very beginning. Now, while a standard natural gas sample is overwhelmingly methane, we're talking about 88%, it's definitely not pure. You've got these tiny traces of ethane, propane, and even carbon dioxide mixed in. And as we're going to see, these heavier elements, they dramatically change how the entire mixture behaves when you subject it to intense subterranean pressure. So how do we quickly classify these different mixtures? Well, the most vital property engineers use is called gas gravity. It's a really simple, elegant ratio. It basically compares how heavy our natural gas mixture is relative to the standard air we breathe, which, if you recall, has a molecular weight of roughly 28.97. To put that into perspective, pure methane has a gravity of exactly 0.55, so it's incredibly light. But if you've got a rich or heavy gas reservoir, one loaded with those trace elements like ethane and propane we just mentioned, that gravity might push well past 0.75. And that single shift is a real game changer. It completely rewrites our flow equations and gives us a heads up that we might be dealing with some highly valuable natural gas liquids. Moving right along to Section 2, the real gas law. This is where ideal math meets real-world pressures. Now, you probably remember the ideal gas law from high school chemistry, right? PV equals nRT. Well, when we introduce the extreme crushing environment of a deep subterranean reservoir, that ideal physics completely breaks down. Actually, scratch that, it shatters. Reservoir engineers have to add an absolutely crucial new variable to this classic equation, the letter Z. Without it, we'd be looking at some catastrophic miscalculations out in the field. This Z factor, officially known as the compressibility factor, is essentially reality's tax on ideal math. See, under immense pressure, natural gas molecules start to interact. They attract and repel each other in ways those basic ideal equations totally ignore. Figuring out this deviation means relying on some complex models. We're talking about the famous Standing and Katz chart from back in 1942, or the highly precise Drenchik and Abu-Qasem mathematical correlation. To actually handle all that complexity, we transform what looks like a terrifying wall of thermodynamics into a simple, three-step engineering checklist. First, we find the molecular fractions. Second, we use those to calculate what we call pseudocritical pressure and temperature. And third, we just plug those right into our correlations to find our Z factor. Just like that, we know exactly how much physical volume our gas is occupying way down in the dark. Okay, Section 3, sour gas and realities. What happens when non-hydrocarbons crash the party? Because let's face it, nature is rarely pristine. What happens when our hydrocarbon mixture gets contaminated by aggressive non-hydrocarbons? In the industry, natural gas without acidic components is known as sweet gas. But if you introduce a high content of hydrogen sulfide or carbon dioxide, our gas turns sour. And while hydrogen sulfide famously smells like rotten eggs, down in the reservoir, it is deadly serious. Sour gas fundamentally alters the fluid's compressibility, which completely skews all those Z-factor calculations we were just talking about. So, how do we fix our math for sour gas? Well, engineers brilliantly use the Wickard and Aziz correlation. Instead of just tossing out our standard charts, this correlation adjusts the temperature and pressure inputs, specifically those pseudocritical values, based on exactly how much hydrogen sulfide and carbon dioxide is present. Once we make that adjustment, boom, we can accurately calculate our Z-factor once again. All right, on to Section 4, flowing through the rock. We're talking gas deliverability and Darcy's law. Now that we understand the gas itself, we have to remember, before we can sell a single cubic foot of it, we need to know what it looks like up here on the surface. Enter the gas formation volume factor, or BG. This metric is a literal translator. It takes that highly compressed, super dense volume of gas miles underground and translates it into the actual volume it will occupy at standard surface conditions. And for the record, that's exactly 14.7 psi and 60 degrees Fahrenheit. This is the volume that actually matters when we're calculating how much gas will eventually heat your home. It's the ultimate conversion rate for energy extraction. So let's look at how it travels through the rock. At low speeds, gas moves to the well in a nice, smooth, predictable manner that's modeled beautifully by Darcy's law. But as reservoir engineers, we want high production. The catch is, once we open the choke on a high-capacity well, that gas accelerates so fast that it enters the chaotic, highly turbulent world of non-Darcy flow. And in that world, Darcy's simple math completely falls apart. Which brings us to Section 5, the turbulence factor. Let's look at these high-speed bottlenecks in the well. We call this chaotic bottleneck the turbulent skin effect, represented mathematically as dq. You can think of this effect kind of like a massive traffic jam at a single highway exit ramp. The faster the gas tries to exit the solid rock and rush into the steel pipe, the more the molecules literally bump into the rock and into each other, creating intense friction. This chaos steals vital pressure right from our well, severely limiting how much gas we can ultimately produce. To actually quantify that penalty, engineers rely on several empirical correlations. Models from researchers like Gertzma or Liu evaluate the rock's fundamental physical traits, things like porosity, permeability, and tortuosity, to mathematically predict just how bad that turbulent traffic jam is going to be. But hey, theory is one thing and reality is another, right? Out in the actual field, engineers calculate this non-Darcy turbulence coefficient using a very practical physical 4-point test. They systematically flow the well at 4 different stabilized rates, measure the bottom hole pressure response for each one, and plot it all out on a graph. The intercept of that line gives them the smooth Darcy flow, while the slope perfectly isolates that turbulent non-Darcy penalty. It is just an incredibly elegant way to build a reliable predictive deliverability curve. And finally, Section 6, transient flow over time, predicting the lifespan of the well. All right, we've mastered the gas, the pressure, and the turbulence. Now we add the ultimate variable to the mix, time. A reservoir isn't just some static tank. As a well produces over months and years, that underground pressure is constantly dropping. To track this, engineers use the formidable diffusivity equation, which beautifully merges Darcy's rate equation with the principle of mass conservation to model transient, unsteady flow. But wait, remember our z-factor? As the pressure drops over time, that z-factor, along with the gas viscosity, is constantly changing too. So to solve this for real gases, especially in deep, high-pressure wells over 3,000 psi, we have to ditch those simple approximations. Instead, we use the brilliant Al-Husseini and Ramy Lil-gas pseudo-pressure function. It's an absolute mathematical powerhouse that continuously accounts for that shifting viscosity and compressibility, completely preventing massive forecasting errors. The payoff for doing all that complex math? We can accurately map out transient inflow performance curves across a concrete timeline. We can see the initial, localized drawdown at 10 days, watch that pressure wave expand deep into the rock at 3 months, and predict the precise yield at a full year as the pressure wave finally hits the absolute outer boundaries of the reservoir. So we've seen the incredible invisible physics used to model natural gas flow. But here is the major takeaway from this explainer. As we deplete those easy, conventional reservoirs, we're pushing deeper into tighter, lower permeability rocks that require massive hydraulic fractures to produce anything at all. In these incredibly complex networks, that turbulent, non-Darcy flow dominates in entirely new ways. Which leaves us with a really exciting question. As underground pressures inevitably drop and turbulence takes over, how will the next generation of engineers evolve these very equations to unlock the fractured energy of tomorrow? Thanks for exploring the depths with me today. Keep learning and keep questioning.